So in this video, I'm going to be talking about how to add vectors together using what is sometimes called the head-to-toe method. And on this slide, what I want to do is just go over two rules of geometry and the notation that we're going to be using. So let's assume that we have a vector and we want to add to it a second vector. Well, as sketched in this triangle here, the resultant is the side that you get by starting at the toe, as you might call it, of this vector, going to the head, and then adding the next vector starting from its toe and going to its end or head. And the line joining the two is the resultant. Now, if we're using the rules of geometry, although these sides are depicting vectors, the lengths of the sides are going to be the magnitudes of the vectors. So the notation that I'm using is that the magnitude of the vector A, I'm just going to write little a for it, and similarly little b will be the magnitude of this vector, so the length of that line, and little c will be the length of this line. The angle capital A is the angle opposite the side A. The cosine rule, which is essentially a generalization of Pythagoras' theorem, tells you that a squared is equal to the sum of the squares of the other two sides minus 2 times the product of the other two sides multiplied by the cosine of the angle which is opposite our side A. And if we want to think about the units of this, let's assume that the vectors A, B and C are all forces, so they'd have units of newtons. That means that their magnitudes also have units of newtons. So here we have newtons squared, newtons squared, newtons squared, newtons times newtons, that's newtons squared, times a number. So all of the terms that are being added and subtracted have units of newtons squared. The sine rule tells you that you take the length of a side of the triangle, divide it by the sine of the angle opposite, and that's the same for all three permutations. So little a over sine capital A is little b over sine capital B is little c over sine capital C. And again, in terms of units, this is newtons divided by a number, newtons divided by a number, newtons divided by a number. So the units all make sense. And what I want to do now is, on the next slide, use these two results and add two vectors together. So here is the example that I want to solve on this slide. We have two forces, one of 11 newtons and one of 8 newtons, and the angle between them is 30 degrees. And to calculate the resultant of adding these two forces together using the head-to-toe method, what we do is we take one of the forces, I'm choosing it here to be the 11 newtons, and do not change that, but then I take the 8 newton force and I add its starting point to the end of the 11 newton force. So that's the head to the toe of the 8 newton force. And the end of the sum of these two arrows is the resultant. So the resultant vector is the diagonal of this parallelogram. So if we look at this triangle, we have two of the sides. This is 11 newtons long, this is 8 newtons long, and we can work out this angle because this is a straight line. This angle is 30 degrees, it's the same angle as there. And since this is 180 degrees and this is 30, it tells us that this angle here must be 150 degrees. So what we can do is use the cosine rule for this triangle drawn here to work out the length of the resultant force, to work out, in other words, its magnitude. So let's just recall the cosine rule. And the cosine rule told us, with the notation used on the other side, that a squared is b squared plus c squared minus 2bc times the cosine of the angle A. And here, this length is going to be little a. This, say, is b, and this is c, or it could be the other way around. And the angle, capital A, will be this angle, which is opposite this length. So this tells us that r squared, this length squared, is equal to this length squared plus this length squared. So that's 11 squared plus 8 squared minus 2 times the product of these sides. So that's 11 times 8 times the cosine of this angle, which, as we've said, is 150 degrees. Now, if we're saying that these vectors are forces, the magnitude of this vector is a force, so we have force squared, that's Newton squared. This is a square of a force as well, Newton squared. C squared, again, a force squared. And this final side, a number times a force times a force times a number. So again, this is also Newton's squared. So everything here is evaluated in Newton's squared. And what we can do is we can just put that into a calculator. Be careful that the calculator is set to evaluate this in degrees, because otherwise we will get an incorrect value. And what we find is that r squared is equal to 337.42 newtons squared. So if we take the square root, we obtain that r is equal to 18.369 newtons. Looking at this, this is under 400. The square root of 400 is 20, so we're expecting something less than 20. That makes sense. And when we take the square root, we also take the square root of the units, so it goes from Newton squared to newtons. And this tells us that to two significant figures, r is 18 newtons. And that is our answer for the magnitude of the resultant force. But forces are, of course, vectors, and we need its magnitude and we need its direction. And what we can immediately see just from looking at this triangle is that the resultant is going to be somewhere in the middle between these two. You have something which is acting to the right and up, and something which is just acting to the right, so we'll get something here in the middle. So we're expecting an angle to be less than 30 degrees between the resultant and the 11 Newton force. So we expect this angle, which I am going to call theta, to be less than 30 degrees. Now, to obtain the angle, I think the easiest thing to do is to use the sine rule. So let's recall the sine rule. And that tells us that A over sine A is B over sine B, which is C over sine C. So in this particular case, well, we've just evaluated this side and we know what this angle is. We know what this side is opposite the angle theta, so we can work everything out for the sine of the angle theta. So we have, if we just rearrange this to obtain the sine of A, so rewriting this, we have sine of A is equal to little a sine of the angle B divided by B. I've just rearranged this. You can either just flip both sides, so you get sine of A over little a is equal to sine of B over little b, and then multiply both sides by little a. So we have this. So in our case, this tells us that the sine of the angle theta here, and little a is the side opposite it, so it's 8 newtons, times the sine of the other angle that we're looking at here, 150 degrees, and that will be divided by the side opposite it, which is r, and we've just worked out what r is. It is 18, but let's use some extra significant figures, 18.369. And we don't need to write out the units, but were we to do so, this is 8 newtons over 18.369 newtons, and the newtons cancel. This is just a number. And if we put that into a calculator, again, making sure that everything is evaluated in degrees, what we find is that theta is the arc sine, the inverse sine of 8 times the sine of 150 over 18.369, and that emerges to be 13 degrees to the nearest degree. So now we have evaluated the magnitude of the resultant force, and we have evaluated the angle theta between the 11 Newton force and the resultant. We've obtained 13 degrees, and that is indeed less than 30. And that sort of check, that visualization based upon a diagram, helps give us confidence in what we're doing and helps us spot potential errors. So to solve this problem, we've used both the cosine rule and the sine rule, and with them we were able to obtain the resultant force. On the next slide, I'm going to give you an exercise to calculate. So here's an exercise for you to calculate using the methods described on the previous slide. Two forces, 8 newtons and 8 newtons, the angle between them is 60 degrees. What is the resultant force? So what I'd suggest you do is have a go at solving the problem, stop the video, and after you've worked out the answer, come back and I will give you the solution. Okay, welcome back. So what you do is you use the methods of the previous slide, and you should find that the magnitude of the resultant force is to the nearest newton equal to 14 newtons, and the angle, well, you actually almost don't need to work the angle out really if you think about it. If you look at it, these two forces have identical sizes, so if you look at a line here in the middle, there is a component from each force pulling in that direction, but the component at right angles to that line from this force and from this force are in opposite directions but equal sized and will cancel each other. So the sum of these two forces, and you're very welcome to check it, calculate it, but the sum of the two forces will be smack in the middle here. So the angle is going to be 30 degrees. So we have, just to draw the picture, 8 newtons, 8 newtons, and the resultant force will bisect the middle. It will be 40, let me draw it a little bit larger, it will be 14 newtons long, and the angle here will be 30 degrees. The angle here will also be 30 degrees. So that's the answer to this problem. Now, on the final slide, I'll just talk a little bit about using this more generally and indicate another method. So supposing you have more than two vectors that you wish to add together. Let's imagine we have three of them, f1 plus f2 plus f3. Well, what you can do is add f1 and f2 together using the method we've described above, and then once you've worked out the resultant here, you could add the resultant plus f3 using the method again. But that seems a little bit tedious, and I would say that the moral to draw from this is that it's simpler to use Cartesian coordinates and vector notation if you are adding more than two vectors. And if you're adding two vectors, you might want to use Cartesian coordinates right from the start. That's really, I think, more of a matter of taste. And I hope this has helped you, and with that, I'll stop this video.